A polyhedron P in Rn is rational if it can be defined by a rational system of linear inequalities. For example, P given by x1, x2 satisfying 2x1 plus x2 greater than or equal to 1 and minus 4x1 plus 3x2 greater than or equal to minus 2 is a rational polyhedron, whereas Q equals the set of x1, x2 satisfying square root of 2x1 minus x2 greater than or equal to 0 is not rational. And if we look at the set of x1, x2 satisfying x1 greater than or equal to the number pi, this is also not rational. Now, a major result in integer programming is the following theorem. If P is a rational polyhedron, then the integer half of P is also a polyhedron. In fact, we can add the word rational here, and the theorem will still be true. So what if P is not a rational polyhedron? If we look at this half space here, the integer half of R is again a polyhedron. It's going to be a half space as well. But one can show that, with some knowledge in number theory, the integer half of Q is not a polyhedron. Now, the case when P is a polytope, that is, the case when P is a bounded polyhedron, is quite easy, because if it is bounded, the number of integer points in P is also bounded. So P sub I is the convex half of a finite number of points which are integral. And previously we have seen a result that the convex half of a finite set of points is again a polytope. We see that P sub I is again a polytope. To prove this theorem in general is quite involved, so we're just going to look at the strategy involved. First of all, one might be tempted to come up with a proof along the following line. Say P is given by x satisfying ax greater than or equal to b, where we may assume A has integer entries, and the entries in each row of A are relatively prime. That is, the greatest common divisor of the entries in each row of A is 1. And one might want to conclude that P sub I is simply Ax greater than or equal to the ceiling of B. Here we are applying the ceiling function to each entry of B. Well, we have seen previously that this is indeed the case when A has only one row. In other words, when this is a single inequality. But in general, this is not true. And if one look at this polyhedron here, this system of inequalities have the coefficient matrix A satisfying the property here. But the right-hand side values are already integers. So if you take the ceiling of them, nothing is changed. But if you sketch the integer half of P, you'll see that it is not defined by these inequalities. So this approach is not going to work. The strategy that can be employed in one of the proofs of this theorem is the following. Recall that if Q is a polytope and C is a polyhedral cone, then P given by Q plus C is a polyhedron. Recall that this is the Minkowski sum of Q and C, and it denotes the set of Q plus C, where Q is in capital Q and C is in capital C. So what we can do is, we're going to show that P sub I can be written as some polytope plus some polyhedral cone C. And it turns out that the polyhedral cone C is exactly the same as the characteristic cone of P. One of the things that one might have to show along the way is the following. If C is a rational polyhedral cone, then the integer half of C is the same as C. As I've mentioned before, this C here is going to be the characteristic cone of P. But what do we take to be our Q? Well, again, one might be tempted to first decompose P into Q plus C, which we know is possible, as we saw in the video when we looked at decomposition of polyhedra. And here Q is the polytope of a finite set of vectors, one from each minimal phase of P. So one might be tempted to take Q sub I to be the Q here. But this is not going to work as the following example shows. So suppose my polyhedron P is as follows. So it's a set of x1, x2 satisfying x1 at least a half and x2 at least a half. And if you sketch this, it's going to look like this. Now this polyhedron has only one minimal phase and is a singleton consists of this point, and this point is 1/2, 1/2. So for this polyhedron, Q will just be the single point 1/2, 1/2. And so Q sub I is going to be the empty set. But clearly P sub I is non-empty, so we cannot express P sub I as this Q sub I plus the characteristic cone C here. So what needs to be done is we need to enlarge Q to include sufficient number of integer points in order for this to work. And there are a lot of technical details involved, and we will not be doing any of that here.